Welcome to Lesson 3 of Module 3 on Convolutional Neural Networks. Today we will cover the architecture of Convolutional Neural Networks, or CNNs. We will then discuss LeNet, as an example of a well-known CNN architecture. CNNs are a type of artificial neural network that is commonly used for image and video processing tasks. They utilize convolutional layers, which apply filters to the input data to detect and extract features. Typically, CNNs also include pooling layers to downsample the feature maps produced by the convolutional layers, and a connected layer with the number of neurons corresponding to the output classes for classification tasks. Recall that padding is a technique used in convolutional neural networks to avoid reducing the size of the input image during the convolution operation. By adding extra pixels around the edges of the image, we can ensure that the output feature map maintains the same spatial dimensions as the input. Convolutions reduce the spatial dimensions of the input linearly with the number of layers applied. For example, if we start with a 224 by 224 input image, we would need 44 successive 5 by 5 convolutions without padding to reach a 4 by 4 output size. This linear reduction in spatial dimensions can make the network excessively deep, which is undesirable. The stride refers to the number of row and column steps taken when shifting the kernel across the input. The main purpose of pooling is to reduce the size of feature maps or inputs without losing a lot of information. This makes computation faster because the number of training parameters is reduced. Pooling reduces the spatial dimensionality of the feature maps while preserving the most important information. This is achieved by applying a fixed function, such as max pooling or average pooling, to small local regions of the input feature maps. Pooling doesn't have learnable parameters because it's a fixed and deterministic operation that is applied to the input data. Pooling is applied to each input channel independently in a convolutional neural network, CNN, because different channels can contain different features or patterns that are important for the overall classification task. In a CNN, each input channel corresponds to a different feature map or channel from the previous convolutional layer. The purpose of pooling is to reduce the dimensionality of the feature maps, while preserving the most important information. Applying pooling to each input channel independently ensures that each channel is reduced in dimensionality by the same factor, which helps to maintain the relative importance of each channel's information. For example, if the pooling operation was applied to all input channels at once, the information in one channel might be overemphasized, while the information in another channel might be lost or downplayed. By applying pooling independently to each channel, the relative importance of the information in each channel is preserved, which can improve the overall performance of the CNN. Over the years, several important CNN architectures were widely adopted by the research community. The first famous CNN was an architecture called LeNet. In this lesson, we will examine the LeNet architecture to understand the key components of a CNN. The other CNNs are modifications of these main concepts. LeNet is a 5-layer CNN. Convolution layers are followed by pooling layers. At the end, dense layers take in the pooling layer's results. Feature maps get smaller in height and width, and the number of channels increases as you go deeper in the network. It can be helpful to look at a simplified view of a CNN that only indicates the network's main characteristics, rather than actually visualizing the number of layers. For LeNet, you can also distinguish between a set of layers that performs convolution and the fully connected block of dense layers. This slide provides a quick introduction to data loader in PyTorch. This construct is commonly found when building CNNs to load and image data. It provides an object wrapper around data. Data loader is usually the most efficient way to load in images. First, you need to reshape input images to 28 by 28 pixels. Then, you construct the network exactly as discussed in the previous section with convolutional layers, pooling layers, and dense linear layers. Between the layers, you can see sigmoid activation functions. CNNs perform feature extraction and outperform most manual efforts in computer vision tasks. However, they have certain limitations. CNNs do not inherently encode the position, scale, and orientation of objects in an image. They require large amounts of data and are computationally expensive to train. Additionally, CNNs do not retain information about the composition or spatial relationships of objects within an image. This can make them susceptible to adversarial examples, where small perturbations in the input can lead to misclassification. Despite these drawbacks, CNNs have proven to be highly effective for various computer vision applications, and ongoing research aims to address their limitations. In the next lesson, you will learn about the trade-offs of depth and model performance. Thank you.